Hello, friends. Here are the solutions to all four of the free response questions from the AP Physics C Mechanics 2025 test, Form J, right? There were probably four different versions. There was one version they released. Here are the solutions. I made four separate videos and posted them one at a time, but here I've got them all together. So here are all four solutions. Thanks for watching, and don't forget to like and subscribe. Well, friends, today I want to go over the first free response question from the AP Physics C Mechanics Test 2025, the released version. There were at least four different versions that I heard about. And so here's question number one. We've got two blocks, and they're moving towards each other, different masses, different velocities. And so we're asked initially to make a chart with showing the velocities, the momentum, the initial momentum, and then the final momentum. The two blocks, they stick together. And so here's the initial momentum of block one, and then just the m, the one that's 1m. So it's 2 v naught m. And then the 6m block, this is the initial momentum of that one. So -6. And so this one goes here. This one's already done for you, right? So they give you the chart. I just drew my own thing here. You're filling in. So the total initial momentum is -4 mv naught. That means that also has to be the total final momentum. So -4 mv naught. So here's the total initial momentum, and here's the total final momentum. That's what they ask you to do here. So it's just -4, right? And so they set the scale here because you've got 2 mv naught, and so it goes two spaces. Each space is just mv naught. So -4 mv naught. So we're going in the negative direction, 4 mv naught. The next thing they ask you to do is to come up with an expression for the maximum force. And they give you this expression that F max is sine A times T. And so in order to find and you have to start with some initial thing. So, some accepted convention, known formula from physics. So we know that delta P is equal to J. So delta P is so the change in momentum is equal to the impulse, and right. And so F is also equal to dp dt. So starting from there, so that means that delta P, right? So this delta P equals, and then the integral of f dt. And we have a function for f, so we're able to put that in there, going from 0 to the indicated time. Okay, but we also want to know what is delta P. So we want to have something to set this equal to once we solve it. So delta P. All right, so the delta P this is of the 6m block, so delta P 6. So it's 6m VF minus -6m V naught. Okay, well, here's the problem. I need to know what VF is, right? I need to find this final velocity, so I can put everything in terms of V naught. Okay, so -4m V naught equals 7m VF. So this is the total final momentum, right? Both blocks together gives us 7m, right? 1m and 6m, and then times VF. So VF equals -4/7 V naught. So I plug that in, and that's what I get here. -4/7 V naught. I combine all this together, and I get 18/7 mv naught. This now is delta P. So I have two expressions for delta P. One, integral f dt, and the other one, 18/7 mv naught. So that goes in here. It goes in here. I do the integral here. I get -fm/a cosine at from 0 to tc. So then putting in my limits, I get -fm/a cosine atc minus cosine of 0. But cosine of 0 is just 1. So I'm going to flip these and get rid of the negative sign. So this becomes -18/7 mv naught equals fm/a, and then 1 minus cosine atc. Solving for fm, this is what I get. So now this is in terms of mv naught a and tc, and everything is good. The next question, so they give you a different situation now. So instead of the first block having some other velocity, it starts off with mv1, or it starts off with v1. So we want to come up with an expression for v1 if together they end with the speed of v naught. They're still sticking together. So the principle that we're going to operate from is conservation of momentum, that the total initial momentum is equal to the total final momentum, right? This is the Greek letter sigma. It means the sum of. That's how I've gotten used to writing that. You can write like pi net, the net momentum. All right, and so we have mv1 plus negative 6 mv naught. Forget the negatives, right? The negatives get a little bit tricky. And then 7 mv naught. I'm not going to try the negative just yet. I'll just leave it here for now. And so now I'm solving for v1, trying to get v1 in terms of v naught. When we solve for v1, we end up with v1 equals 13 v naught. Okay. Now what if, so this makes sense. So v1, so they end up, um, uh, yeah. So, but anyway, if we make v naught negative, just watch. If we make v naught negative, and we plug this in, what happens? So this would be 6 mv naught, and then minus. So this would be 1. So v naught, or this would be -1, right? V naught, negative v naught would be v1, which would mean that the 6m block and the 1m block were both moving v naught. There would never be a collision. They would never actually hit each other, right? But we know that block 1 is moving right initially, and so this can't be the possibility. So we know it's moving to the right, and so here's our expression: v1 equals 13 v naught. So that's the first question. Now we're looking at question 2 of 2025 AP Physics C Mechanics free response questions. So this one involves some springs. We've got 2 springs on either side attached to a block, and one has spring constant K, the other 2K. And so what I did, if you have this on paper, you can just write on it. What I like to do, and so I encourage you to use lots of scrap paper when you do this kind of thing. So I want to draw this for myself because I want to notice the details. I want to take notes on here so I can write K, 2K, all this stuff. And then right below it, I draw what's happening, right? So this is moved to X. I know, beautiful artwork here. Such convincing springs, but you'll have to move past that admiration to do the physics. So when this is brought to X equals X1, so they want to know, basically they give you a bar chart and they want to see, can you quantify and compare the potential energies of the springs in the springs and the kinetic energy. So the potential energy in spring A, 1/2 kx1 squared, and then potential energy in spring B. Spring B is 2k, is the constant, so it's 1/2 2k x1 squared, so that's just kx squared. And the kinetic energy is 0. It's released from rest at that point. When we draw the bar chart, that means that UB should be roughly twice as high as UA. You've got the grid lines on there on the response paper, so you should be able to get that. And then K should look like 0. Okay, so that's question part A of the question. Now it's released. Oh, and they want you to find an expression for the velocity when when the block is at position x equals 1/2 of x1. Okay, and so what we do is we set up the conservation of energy equation. The potential energy plus the kinetic energy plus the work in the beginning. So, but there's no work here, so we leave that out. Equals the total energy at the end, UF and KF. I found the effective spring constant here rather than finding the 2 potential energies separately. I just found one potential energy. It's basically like having springs in parallel, and so the effective spring constant is 3K. It's just K plus 2K. We get 3K. So the total potential energy is 1/2 3kx1 squared. No kinetic energy in the beginning. At this point where it's halfway, so it's 1/2 3K 1/2 x1 squared plus 1/2 mv squared. We don't know v. In fact, v is what we're looking for. We just leave the m in there. This is just solving a bit of work, algebra, nothing too complicated, but I wanted to kind of write out my steps as I was doing this, and I end up with this expression that 9/4 kx1 squared over m equals v squared. Take the square root, and we simplify, bring out the square roots that I can take, and I get v equals 3x1 over 2 times the square root of k over m. Good. So one thing to check here would be interesting, right? So k, what are the units? Well, k, the units on k are actually interesting. It's they are kilograms per second squared, and then divided by m. So this is all in the square root, right? And then the m is kilograms, and we've got the x on the outside, so it's meters. This simplifies. You get kilograms canceling out the seconds on the bottom, square root, meters per second. That's velocity. That's what we want, just to kind of check what's going on with the units. Part C, so now we've got, this is on a, um, it's on a new surface. They give you the graph in scenario one, where it's just oscillating back and forth on a frictionless surface. And then scenario two, it's on a new surface where there is friction, but they tell you that the period's the same. So we want to take note of that. And again, if I'm doing this, I want to see these two um, graphs, one right above the other, so I can line them up. Right? I don't know exactly what it looked like on your answer key, or not your key, but your answer booklet where you're putting them. But I would want to, uh, get this where everything is lined up, so I can just draw one graph right below the other. Now, the graph they give you is position. The graph they ask you to make is kinetic energy. The thing about kinetic energy is it's never negative. It's always positive. Because there's friction, the kinetic energy is going to be decreasing. And so the minimum kinetic energy is going to be when it's at maximum position. And when it's passing through the equilibrium, zero position, that's where you have the maximum kinetic energy. So I drew dots, I've got my zeros where I'm at maximums and maximum min position, you could say. And I have maximum kinetic energy lined up with the zero position here, right? I tried to. And then these are just getting smaller as they go down. Part D. Relatively simple. They just say that, okay, now we've got a new block, larger mass. What's one thing that's going to change about the graph? Well, we have this equation, period is 2 pi root m over k. So if with no other analysis, just from this, we can say that the period is going to increase. And so that's going to be a horizontal dilation and stretching of the graph, right? So increased m, increased mass, increased period. It's a stretching of the graph. Okay, today we're looking at question 3 from the 2025 AP Physics C mechanics test. This is the released version. And so the question has there's a pendulum and it's got this box on it, this open, what do they call it? A box, yeah. And so then there's a block inside. So the pendulum swings and then it hits a stopper, and the box, the block slides out of the box. And so they tell us that we have a meter stick and we have a motion sensor, and we have to design an experiment using this equipment to find the value of G, acceleration due to gravity, on the surface of the Earth. Okay, so when I was an AP physics reader, when I graded the AP test, it was AP Physics 1, and it was an experiment design question. And honestly, I think that question was harder than this one, but that's neither here nor there. So some key things, you want to mention the equipment that you have, um, and you want to describe how you're going to use it. So I said, I'm going to use the meter stick, so I'm naming the equipment, to do what? To measure the height before the block is released. Okay, great, right? I'm specifying before the block's released. What am I measuring? I'm measuring height. And then I'm going to use the motion sensor. I'm identifying the piece of equipment to measure the speed, right? So that's the quantity of the block as it leaves the box. And then I'm going to repeat this for various heights. So I'm telling you what I'm going to use, how I'm going to use it, and the data that I'm going to get. And then I'm talking about, doing that multiple times. So that's part A. Part B just says, describe how the data collected could be graphed uh, to be analyzed to determine the value of G. What we're usually looking for here is we're going to find the slope, that the slope of the graph is going to reveal to us G. We're going to be able to use that somehow, some like constant times the slope to give us the value of G. Well, I'm starting with my equation, conservation of energy. So initial gravitational potential energy equals the final kinetic energy, so mgh equals 1/2 mv squared. Solving for G, because that's what I'm trying to find, I end up with G equals Vf squared, so the final velocity squared, over 2h. All right, so what does that mean? That means that I can use the square of the velocity as on the vertical axis, and I can use the divided by the height, so that, right, because it's rise over run. And then I can take half of that, right, and then the height will be on the horizontal axis as the independent variable, you could say. And so then if I find the slope, I just have to multiply that by 1/2, and that'll give me the value of G. Now, that's not the graph that they give us. There's a different graph that I end up having to do later but this describes how I could use these values to get the value of G. Part C asks now, we've got a new scenario, and they give us some data. In this case now, it's the block lands on a friction surface and it comes to a stop. Okay, so we're in conservation of energy mode. And so we're always thinking like, what am I going to use? Conservation of energy? Am I going to use dynamics? Am I going to use momentum? Here we're continuing our thought using conservation of energy. And it's real simple. It starts off, the system starts with some gravitational potential energy. And then there's some energy lost due to friction, a non-conservative force, work done by a non-conservative force. And then I end up with zero energy at the end, right? And so I put in my equations. So I set UG equal to the work done by friction. So MGH equals mu mg times X max. X max, that's what they give us, right? So we got to use it in terms of what they tell us. So when I solve for mu, I end up with H over X max. And so mu, if I put H on the vertical axis and X max on the horizontal axis, then I can find. I saw some other AP teachers, they had some different solutions, but I think that this should work, right? So that's part one of part C, just doing that. Two is actually doing the graph, part two, right? They say to plot, plot the points. And so they give us the points. So I plotted them out here. And then part three is a best fit line. So here's the best fit line. Three, tried to put it through the center of the points. I'm trying to not go beyond the points that I have. And then D, now I have to use the slope to calculate the uh, the coefficient of kinetic friction. And so I find 2 points that are easily identifiable, pretty close there to those, those grid lines, those grid line intersections. And so here's this point, here's this point. Now I find the slope formula. And when I do that calculation, I get 0.43 as the coefficient of kinetic friction. So experimental design, data analysis, standard fare for a AP physics test. So, hello friends. What we have here now are the solutions to open-ended question 4 or free response question 4 from the 2025 AP Physics C mechanics test. The first question, so we've got two objects, a disk and a ring, and they're both rolling towards the same ramp, and they're going to roll up the ramp. Same material, same mass, same radius, all those things. And so they tell you that the ring goes higher up the ramp than the disk does. So they want to know which of these or they ask you to compare the force of static friction with between the two of them. Now, one thought I had as I was thinking about this was, oh, it's going to be the same because it's just the normal force times the coefficient of kinetic friction, and it's the same mass, same radius, so this would be the same normal force, the same material, all that stuff. However, that equation, right, mu times n, that's the maximum static friction. That's not what the static friction is necessarily, but that's the maximum static friction. So that's not how to think about it. Instead, think about it this way. We have the static friction force is going to be this way. Here's what you can think. So this thing is spinning clockwise, right? But when it gets to the top, it stops. That means the torque has to be pushing counterclockwise. What's doing that? That's the static friction force. The static friction is actually pushing uphill. And then you've got mg sine theta pulling downhill. So translationally, the bigger static friction force is going to make the object go higher up the hill. And which one is that? That's the ring. Right? And so that's what I kind of explain here, that friction force is directed uphill. So translationally, the ring makes it farther up. And so the ring must have a higher static friction force. And so that's what's indicated here with those symbols. The next thing they ask us to do is to find an expression for the static friction force uh, using I and M and R, theta, and any other physical constants, like, for example, the acceleration due to gravity. Always start with a good force diagram. So here I have mg, the static friction force. I have a little triangle here so I can see where the angle is. This is mg sine theta pulling down. So I write out Newton's second law, sigma F equals ma. So the sum of the translational forces equals mass times acceleration. And it still works, right? Translationally, Newton's second law should still work. putting in my forces. So I have the static friction force this way and mg sine theta. So that's the right that component of the earth force pulling down that way equals ma. The direction here is a little bit interesting. The acceleration, we say, well, that's downhill. So why would we put the negative in here? And the thing is, this a that we're going to put in, that we're going to substitute from over here, is the acceleration from the torque, right? And so, and it actually does end up working out. This is a negative thing that gets put in there, but also we have to check at the end, and I'll show you how that works out. We always want to check our signs, check our answers. So anyway, we have that, and then sigma tau, so the sum of the torques equals I alpha. Okay, what's the torque? R cross F. If we take the center of mass as the axis of rotation, then we have the friction force. That's what we want to find an expression for. So we substitute that in R cross F, but the order doesn't matter in this case because theta is 90 degrees, so sine of theta is 1. And then so I, instead of alpha, we substitute A over R. So A, now we substitute, or we solve for A, because this can then be plugged into this. Notice A is not one of the things that we can have in our final expression, so we're going to substitute that out, get rid of that. The rest of this now is just solving for Fs. So I bring the terms with Fs together on the same side, I factor out Fs, and then I divide, and I get this expression for the force of static friction. So let's think about this for a minute too. We want to check this out. I is on the bottom here, so it's mr squared over I. So if we have something like a disk as opposed to the ring, so a disk is 1/2 mr squared, has a smaller moment of inertia. And so we had said that that has a smaller um, coefficient or smaller force of friction, right? So if we have 1/2 mr, so mr squared over 1/2 mr squared, this becomes 1/2 in the bottom. So this becomes 2. So 1 plus 2, that's bigger than what it would be otherwise. And so we have a bigger thing in the bottom. So the overall expression is less. So for a disk, we have a smaller static friction force than for a ring. And that's what we said, right? Disk is smaller than the ring. So that works. If we end up with a negative sign down here, playing around with the sign and trying to figure that out, I ended up with a negative sign. I ended up with 1 minus mr squared over I. Well, if you have a ring, then I is just mr squared. Mr squared over mr squared would be 1. And in that case, you have 1 plus, or 1 minus, if there's a minus sign there, 1 minus 1. That gives you 0 in the bottom of a fraction. And that's when the universe implodes, because you can't have 0 in the bottom of a fraction. And then you'll never find out what score you got because the universe won't exist anymore. So best to make that a plus sign. C, so here they ask you to find, or to think about how the coefficient of kinetic friction would compare if, for example, they had some objects and they changed the surfaces so that there was slipping as they hit the ramp. And the answer there is that it would be the same for both. In this case, we do use the expression mu k mg cosine theta. Mg cosine theta gives us the normal force, and that's the same for both. It's the same angle, same mass. It's the same mu because it's the same material that they both have. And that means then that the force of kinetic friction is the same for both. So that's it. The challenge, of course, is figuring out this stuff about the direction of the torque, the direction of the static friction force, doing the solving, paying attention to those signs. But it should all work out. Pay attention and check your answers, compare them to one another as you go as well. So thanks for watching. Don't forget to like and subscribe.